Hi, and welcome to this session on planning JWST multi-object spectroscopy observations with the NIRSpec MSA Planning Tool, or NBP. My name is Diane Karakla. I'm with the NIRSpec Instrument Science team. The MOS mode on the NIRSpec instrument uses the microshutter assembly as the hardware for this mode. The microshutter assembly consists of 4 quadrants, each with many tiny little shutters that can be configured to open slits on objects in the field of view. The entire array has about 250,000 shutters. The shutters are separated by little bars between them. Each of the shutter doors can be opened or closed to configure those slitlets. Each shutter is only about 200 by 450 milliarc seconds. The entire field of view is about 3.6 by 3.4 arc minutes. The picture to the left shows the 4-quadrant array. It resides on a mounting plate. Also located on the mounting plate are the fixed slits, apertures, and the IFU aperture. This figure shows the MSA projected against the 2 NIRSpec detectors. And there's a gap between those 2 detectors. The outlines in red show the actual detector areas. The spectra are observed through the slits in the microshutter assembly, and then they are dispersed from left to right across the 2 detectors. And so it's very important to mention the gap, the detector gap, because in any given exposure, some of the target spectra will be missing different wavelengths, and the wavelengths that are missing depend upon the location of the slits in the microshutter assembly. So there's a planning tool that we've created to help plan around these obstacles. First, I want to say some words about the MOS observing process. It entails a multi-step process, and that is because we need to be able to assign an aperture position angle for the flexibility of scheduling MOS observations, and final plans can't be made until that aperture position angle assignment is made by Space Telescope Science Institute. So the way it will look is as shown in this timeline. For the proposal deadline, the observer will submit placeholder visits for the NIRSpec observations, and they will use the MSA Planning Tool to help accurately estimate the overheads and provide any observation links that are needed in order to put them into the long-range plan. The long-range plan is constructed from those successful programs, and at that point in time, the aperture position angle is assigned to those programs. Following that 6-week period after the assignment of the APA, NIRSpec program updates are due. And these are the final program updates using the assigned angle and observing specific sources that the user intends. If any further program updates are required, say, for example, the operability information about the shutters changes, and if there's a serious impact, we'll communicate that to the observer. That may require an update to their program. So if any of these program updates are required, the final programs are due 4 weeks in advance of the start of the observation window for the NIRSpec MOS observations. Generally, targets pointing at different pointings in the sky for James Webb will have 2 windows of target visibility. These are produced by using the target visibility tool, or it may be done from APT itself using the roll report in the visit planner. And so what you see here is a figure of those feasible angles for any given pointing that are available during the cycle. And generally, like I said, there are 2 of them that are separated by about 180 degrees, and there's a short period of feasibility here. And this is another a listing here by date of what angles are feasible. These are V3 position angles. It's a little bit different than the aperture position angle that we just discussed. They are related by just an offset of about 138 degrees for NIRSpec. The NIRSpec aperture is tilted with respect to the field of view of other instrument apertures on James Webb. So now a word about positional accuracies, target acquisition, and pre-imaging. The positional accuracy of your input catalog will has to have the required relative positional accuracy of less than 15 milliarc seconds in order to place the sources into these tiny shutters with accuracy of about a tenth of a shutter. Larger relative accuracies are possible. You can do MOS observations of those as well, but that is not advised if you want to have good knowledge of the centering of your sources within the shutters. If you don't need that level of accuracy, it's possible to do MOS observations with less relative accuracy as well. Generally, this level of accuracy that we're talking about here, in order to do optimal planning, is acquired from HST, ACS, or wide field camera 3 imaging. And that should be more than sufficient to give the 15 milliarc second accuracies. So target acquisition for this mode consists of placing candidate reference stars into some shutters and then centroiding on those reference stars, and then repositioning the telescope slightly to make sure that the sources in the field are accurately placed into the shutters they were intended to have. The MSA TA requires about 5 to 8 reference stars. 5 is minimum. People should always request 8 or as many as possible in their field. Again, 8 reference stars are optimal. It will give the accuracy needed from the MSA target acquisition to be able to observe the MSA sources of interest. NIRCam pre-imaging. So NIRCam is the imaging instrument on James Webb, and it's possible that if you don't have observations that are deep enough and accurate enough from, for example, ACS or wide field camera 3 images, then you may need to go out and get these, to request these images in your proposal. This would be in your first phase proposal that you would need to request these. So that will have to be a decision that's made upfront based on what's available in that field of view. So the reference stars that will be drawn from the same field as your targets. So and the stars can be no brighter than 18th to 19th magnitude. And also, another concern is that you want the area to be large enough to allow for any aperture position angle that you may be assigned for your MOS observation. So for NIRCam, or for any field, you would want a 5 by 5 arc minute field of view minimally. For NIRCam, that means typically a 2 by 1 mosaic and some dithers to cover the gaps between the modules. And then, again, the accuracy needs to be better than 15 milliarc seconds, and NIRCam will deliver that level down to 5 milliarc second level of accuracy. So this is an image of a mosaic with NIRCam. There's an actual tool that's a standalone tool that's been developed by one of the members of our team. It's called the NIRSpec Observation Visualization Tool, and that's available online for you to help plan your NIRSpec and your NIRCam observations of the same field at different times of the year. One thing that I wanted to mention is that when you do, I mentioned that you need to insert these NIRCam observations, if you need them, into your first phase of your proposal. They need to be fully specified at that time when you propose, because it has to go on the schedule, and that'll have to be pretty autonomous. We'll have to be able to execute that in the first visibility window, for example. So the process with NIRCam pre-imaging looks almost the same, just a tad different. Instead of the 6 weeks following the assignment of the aperture position angle, there'll be a little more time involved to do the actual NIRCam observations. And then after the NIRCam observations, you'll have 6 weeks to do the program updates for your MOS observation. So for best success, we advocate using a special requirement in your proposal to separate those two observations, the NIRSpec and NIRCam observations, by a good deal of time to allow for you to have enough time to plan the update, the program update, and for us to basically get the products that you'll need correct for the NIRCam observation. The geometry has to be worked out in commissioning, etc. If it's not possible to separate those, if it's not possible to separate those observations into the two visibility windows, then at the very least, you must have a program update due 4 weeks in advance of the start of the observing window for the NIRSpec. Okay, so I'm going to be demonstrating the MSA Planning Tool in APT. I'll be using the latest released version of APT, which is APT 2020.1.1. It's available from this link, and I will be doing that in just a moment. First, I want to give a little overview of it. So we have addressed some user concerns. In the past year, because of the one-year launch delay that we had, we used that time to improve the performance and usability of the tool. So it's a lot more intuitive. Things are located in the right position in APT now. The tool is actually an official tool. It's found in the toolbar of APT right there. So I will be demonstrating how to use that in a bit. Okay, so first, I have a few slides to basically describe what the planning tool is going to do for you and how it works. So again, there's a fixed grid of shutters and micro shutters in the MSA, and they are separated by small bars. And if a source lands behind a bar, you're not going to see it. So one of the things the tool does is it makes sure that the sources are falling into the shutters before it selects those sources for observation. There is, like I said before, a gap between the two NIRSpec detectors, and so that will possibly require dithering if you need to pick up the wavelengths that are lost in any given exposure. If you want to observe them in a second exposure, you would have to dither a little bit in order to recover those wavelengths that were missing. Again, the MSA has failed shutters like any other device that we make. The failed shutters may be failed for different reasons, and there are also shorts between the rows and the columns that have to be avoided during planning, and the MSA Planning Tool will take care of that for you. The source positions also require knowledge of the optical distortions in the telescope and in the instrument, and velocity aberrations that are caused by the movement of the telescope with respect to the pointing that it's looking at. So we take all of that into account. We map the positions of the sources to the microshutter array, and then open appropriate shutters there to create those MSA configurations. And I will just say that this is not an easy task. It's easy for one pointing position, but it's not easy when you're trying to track sources through a number of pointing positions, through a set of dithers. That's the hard part. Failed closed shutters look like these, what are sprinkled all over the MSA, these black little dots all over the MSA. And sources, we don't select sources that fall on them. The shorts look like these columns and rows, a sort of a plaid effect there. We try to avoid those as well. The failed open shutters are the ones that will really get you because there are about 20 of them, I think 19 in the visible area of the MSA. And these are potentially going to cause contamination of your target spectra. So we mask areas of the MSA that are affected by anything that would be caused by a source in one of these open shutters. We mask out those areas on the MSA and plan around them so that you don't have contamination. There's also a button in the planner of the MSA Planning Tool where you can just elect to instead use these open shutters if you'd like to. They're just poorly calibrated. So again, at each test pointing, this tool will create a series of test pointings in a grid on the sky, and you'll specify the spacing of the grid and the extent of the grid, and that at each pointing, the tool will try to plan around the failed shutters, pick up as many sources as it can through all of the dither points. And so it's optimizing the use of the MSA as much as possible, but while also observing as many sources throughout the dithers as possible. Okay, so what you'll need to run the MSA Planning Tool is an internet connection, and that allows you to get the most up-to-date MSA shutter operability information and to check for guide stars, suitable guide stars in the pointings that you're planning. Also, you'll need that input astrometric catalog. And again, the source positions have to be accurate to less than 15 milliarc seconds in order for the use, really the optimal use of the MSA target acquisition. The source catalog must also be complete. And I say this because we don't do any contaminant avoidance during planning. So it's left to the user to check that other sources are not contaminating their slits. And so I'll show an example of that at the end of the demo, or near the end of the demo. Okay, and the products that NBP produces are plans, what are called plans, and those plans are turned into, you'll select the plan and turn it into an actual observation, and it will populate the observation template. Along with that, with these particular pointings, of course, you have particular MSA configurations, and then the set of sources that are observed through that set of dithers is called a target set. So that all that information is tracked by the MSA Planning Tool. So next I want to talk about the source catalog requirements. So the first step is to create this catalog of sources. This catalog should be complete. It should contain all known sources in the field. And the reason for that is that you want to be able to check whether the plan sources that you're creating spectra for are impacted by the unintended nearby sources that happen to fall in the same slit. You want to be able to check that. The tool itself does not plan around contaminants, so you have to double check that in your plans. The catalog is just an ASCII file. It has to contain J2000 RA and DEC minimally. It should also have target IDs, source IDs, and the observed targets will, of course, be derived from this listing of candidate targets. The header in the file is optional, but it helps to instruct the MPT during the ingest of the catalog. It helps to instruct MPT what the catalog, the columns contain, what type of data the catalog columns contain. Okay, and so because of the small size of the shutters, again, you want between 5 and 40 milliarc seconds are the usable accuracies, and that will depend, whether it's usable or not, will depend upon the science that you want to do. So for moderately extended sources, you might be able to get away with 40 milliarc seconds in the relative astrometric accuracy. But less than 15 milliarc seconds is for optimal TA planning and observation with the MOS mode. So next I'm going to show you an APT demo on how to ingest an MSA catalog into APT. Okay, I have APT already started, APT 2020.1 already started. I'm going to start by showing you how to load a catalog. But before that, let me just say that I got this menu here by selecting New JWST Proposal. And then what you see is this menu here, okay? So the first thing you'll want to do, well, is, of course, fill out your proposal information. I'm not going to bother with that because it's of no consequence for the demo. I'm going to go to Targets, and you have a series of selections of different types of targets you can enter. For the MPT, you'll want to define an MSA source catalog type target. So when I press that, there's a pop-up window. I'm going to browse to my catalog. And I know the name of the catalog is the HUDS. No, I'm showing you good stuff. Hold on. Good. Let's see. Here it is. Okay, so it self-populates the catalog name. We'll let that go. And I'll put white space separated as the format that this particular catalog has. So you can see that it automatically tries to identify your column for you. These set of values here were entered with the catalog. It's an ASCII catalog, and it had a header line that said what each of the columns was. And so the tool was successful in being able to identify that this is the ID, the source ID column. RA and DEC are here. That's a magnitude. And so it can understand certain columns. One that it didn't pick up was the redshift because it's named in a funny way. So I'm going to tell it that it's a redshift. And we're going to use that redshift. So everything else is defined. I'm going to say import, and it shows you the progress. And immediately it tells you there's a red X, there's a problem. Okay, let's look at the first red X. It's this here. It doesn't like underscores. So what I'm going to do is get rid of this whole thing and just put that as my catalog name. You can rename it to whatever you want to do. Okay, so now it's happy with that. I'm going to highlight the catalog, and it wants more information. It wants the level of accuracy, relative astrometric accuracy. I'm going to put 10 milliarc seconds because it was generated from ACS data, I believe. And then I'm going to say this is a field that's already observed by GOODS. So I'm going to say that the data are already obtained. The pre-image availability is already obtained. And this is just a way of linking. It tells APT that there's an existing image from which the catalog was derived, and helps to link that information together in the archive. So now I have this entire catalog. It's huge. And so, actually, I don't even know how many sources it is. It should say, I don't see it here. But I'm going to derive a subset of that and use that for the planning in the MSA Planning Tool. So I'll say new candidate set, and I'll give the new candidate set a name first. I'm going to choose redshifts greater than 5 as my primaries. So I click Add Filter, then New Redshift Filter. My minimum redshift is 5. I click OK, Make Candidate Set. And now I have a new entry here. It is a daughter of the catalog. And if I click on it, the data from that subcatalog or that candidate set is shown. It tells me that I have 542 sources in this subcatalog or the candidate set. Okay, those are the items those are the ones that are with redshift greater than 5. Now I'm going to create another candidate set because the MSA Planning Tool works with two different candidate sets, a primary candidate set with your high priority sources and a filler candidate set. So I'm going to now define a filler candidate set as click New Candidate Set again, and this time it's just going to be redshift, everything with redshift greater than 3. So now this candidate set is going to actually include the sources from the primary candidate set. Do it the same way. I select the redshift filter. Redshift has to be greater than 3. Okay, make candidate set. Okay, so now I have two candidate sets, and I'm all set to go. In this section of video, I'd like to introduce the NBP Planner. The NBP Planner is really the guts of the MSA Planning Tool. In the MSA Planning Tool, there are the screen like this. There are two tabs. The first one is the Planner. The second one is Plans. The Planner is really the engine for generating your MOS observing strategies or observing programs. It allows you to select several different parameters, and you just go through in sequence and make selections in the Planner to define your observing plan. The first thing that you'll have to do is choose the primary candidate list. Here I'm showing the catalog that I generated the candidate list from and the two candidate lists, redshifts greater than 3, redshifts greater than 5. I've selected the primary candidate lists in this shot, and now I have to select an aperture position angle to test with. So I selected one that I know is a feasible angle for this catalog. Next, I choose the slit setup parameters. The first parameter that we have to decide is what is the default length of the slitlet to use for each of the sources in the field of view. In the case of point sources, we nominally recommend the 3-shutter slitlet. That allows the target to be in 1 shutter at a given time, and then 2 shutters are used for background estimation. Secondly, there is a source centering constraint. A menu from the pull-down lists 1, 2, 3, 4, 5 different values of a margin that can be applied as the source centering constraint, which keeps the sources inside the margin. So let's talk for a moment about what the margin is going to do. What you're seeing here is an image of 5 different images of a monochromatic PSF generated at each of the wavelengths shown under the image. And it's cut off by the shutter, the shutter dimensions. In this sequence of images, the source is actually placed off-center, so you can see what a typical MSA source PS point spread function would look like. So you can see that the slit throughput is going to be a function of not only the wavelength and the width of the point spread function, but also of the relative placement of the source in the shutter. So the margin, the source centering constraint margin that we're talking about in the planner, allows you to select sources that are more and more confined constrained to be closer to the center as you go down this table here. Also, we've shown the minimum relative flux transmission at roughly 3 microns, just to give you a comparison in physical units of what the effects are on the throughput, on the slit throughput at that wavelength. And you can see that it ranges from 12% with almost no margin to 85% as the minimum relative flux transmission. So this is relative to the source centered in the shutter. So as you can see, a tighter constraint results in a higher flux for the source, but it may also result in fewer targets that are observed. So next I want to talk about the benefits of dithering. In addition to improving the sampling of the PSF and correcting for hot or bad pixels, dithering also helps you to improve background subtraction. Recall that I said in a 3-shutter slitlet there would be 2 shutters for background estimation, 1 for the target spectrum. And so you can see in 3 different exposures we've tilted the telescope, we've nodded the telescope a little bit. This is called nodding. It is a parameter in the NBP Planner which you can enable or turn off. And the result is that for a 3-shutter slit, you'd get 3 exposures with the target in each of the different shutters of the slit. Additionally, you can recover, for example, lost wavelengths that maybe fall in the detector gap by using a fixed dither. This is a second option. The 2 options can actually be used together. You can do both nodding and dithering. The dither allows you to move the sources to a different part of the detector, the source spectra. And so you get additional exposures with nodding if you have elected to use that at a different dither point on the MSA. And to do this, you are the fixed dither requires a reconfiguration of the microshutter assembly. So that will be an overhead that you will have to pay for that large dither. You can, in doing so, you can observe additional sources behind the bars or that were behind the mounting plate in the earlier set of knotted exposures. It also helps to mitigate the effects of light leakage through the MSA because each of the shutters in the MSA have a finite contrast, and they're all different from one another. They're all roughly 10,000 or better, but there are small light leaks that can occur, and one of the ways to mitigate this is by moving the sources to a different detector location, or perhaps even a different location with respect to the shutter itself. The edges of the doors have small light leaks that can happen even on a shutter, on a smaller than a shutter basis. So NPT is the tool that will actually take all of the dithers into account and will attempt to observe as many sources as possible through that set of dithers. So that's actually the hard part, is tracking the sources through the set of dithers. But NPT does that for you. So how does this actually work? What happens is NPT starts by creating a grid of test pointings over the area of the primary candidate list. And it uses the user-specified search grid parameters, so both the extent, the height and width, and the cell size of the search grid are specified in the planner. Then the sources are mapped to the MSA plane. I'm just talking about the primary candidate list at this time. At each pointing, NPT then checks each source in the primary candidate list, and it does so in the order that they're listed, which turns out to be important. And unless you also select to do shuffling, which we'll talk about later. So what NPT tries to do is it tries to place the sources one at a time into the MSA configuration. It checks them at all dither points. It checks their background shutters at all dither points, and it makes sure that the shutters that are all operable, that need to be operable, and it makes sure that there are no conflicts with other selected sources. So therefore, that's where the ordering of the sources in the candidate list matters, because if you place a source down on the MSA, it prevents other sources nearby from also being selected for the same exposure. So there is a sequence to this. So it generates what we call a heat map. This is a grid of all the results of testing those viable sources, how many sources it can put into the MSA configuration at each of the test pointings from the search grid that you've defined. So the weights of all of the primary sources, if weights are used in the planner, the weights of those sources are summed at that grid point and then are inserted into an internal heat map and kept track of. So eventually, you can see where I'm going with this. These brighter areas of the heat map are preferentially the ones to select, that NBP will select for you as the best pointing to obtain the most sources, and certainly those of the highest weight if weights are used. This is just showing a zoom in of a small area of the heat map. On a very small scale, you can see that there is still structure, even at the shutter scale, within the shutter scale. So when you're doing your NBP testing, and it's certainly fine to do a coarse grid sampling on your heat map or on your search grid to begin with, and then but when you're finalizing your plans, it actually may pay to do a fine sampling of the heat grid to see basically if there are improvements in the number of sources that you can obtain. So NBP then selects the best pointing from this heat map, and it will do this selection for the entire set of dithers. And then these results are solely based on the primary candidate list, as I mentioned. The primary candidate list is the one that drives the pointing selection for your plans. If fillers are added, that is a secondary step. So I just wanted to point that out. So the MSA configurations for each of the major dithers then in the plan are built, and then the filler sources are added in after the fact. A plan is then generated in NBP. Plans have pointings and sources that will be observed at each of those pointings, which we call a target set, and associated MSA configurations that NBP generates for those pointings. Then the user will select one or more of these plans to generate a MOS observation from. So now I'm going to demonstrate the planner, the use of the planner, and the generation of plans, and how to evaluate those plans in the Plans pane of the MSA Planning Tool. Now we want to use the MSA Planning Tool. We want to go directly to the MSA Planning Tool. We don't go to the observations. That's going to be done afterwards. So let's go to the MSA Planning Tool. It's up here in the toolbar. Okay. The first thing you'll notice is that there are two tabs in this MSA Planning Tool. The first one is MSA Planner, and the second one is this Plans area where you will evaluate the plans that you've made against one another. Okay, so I've already it remembered it remembered the values, but you would just select from these pull-down menus whatever candidate sets you've defined. Now, in this particular case, I showed you how to read in the Good South, but I'm going to actually be working with the HUDF catalog that I preloaded. So it was already baked in the cake there. So let's work with the HUDF. I'm going to select my primary candidate set, which is the redshift greater than 5 sources, and I'm going to select my redshift greater than 2 sources as the filler candidate list. Both lists have to come from the same catalog. You cannot plan an observation, a MOS observation, from 2 separate catalogs. I just want to make that clear. The first thing that normally you would see here is 0. And so I'm going to let it try to select 0 to show you what will happen. So this little twirly thing here is telling you that it's trying to get a guide star, look for guide stars that are suitable guide stars in that area based on the catalog that you gave it, the candidate sets that you gave it. So it gets a red X because that is not a successful or a feasible angle. And the feasibility, the general target visibility tool will give you the feasibility of different angles for your source. For this particular field, I know, for this particular pointing, I know that 135 works well. So I'm just going to use that, and it should get rid of the red X. Yeah, okay. So now we define the split setup. The split shapes that you have available to you as default split shapes are these 4 selections, 1, 2, 3, and 5 shutters. If sources are point-like, we normally recommend 3 shutter slitlets for that, for those types of sources. So I'm going to use that because these are distant galaxies. They're probably going to be most likely point-like. Now you have the option to constrain the centering of your sources. As the sources get further and further towards the edge, it affects the flux calibration, of course. You have more significant slit losses. I will show you a slide on that when we get back to the slide. So I'm going to select the midpoint for this, just to demonstrate this. I did in that. Did I select midpoint? anyway, we'll leave it at midpoint. I am going to select the dithers next. The pointing setup is the next section. I want to nod in the splitlet, which means that I'm going to get 3 different exposures where the targets are going to be placed in the first exposure in the center of the splitlet, but then in the next exposure, targets will be at the top, and then in the final exposure, targets will be at the bottom. And the reason for this is dithering helps with all of the pixel-based artifacts that are on the detectors. So this nodding, it basically is coming for free. It's a very slight movement of the telescope. You don't have to reconfigure the MSA in order to get this. So no overhead from the MSA reconfiguration for this. I'm going to define that I also want to dither by more than just nodding. I want to actually reconfigure the MSA in a few other places. And that helps to, for example, across the gap between the 2 detectors, as I mentioned before. That's one of the reasons why you might want to dither. Another is to place those sources into different areas on the detector to wash out over any quantum efficiency differences between different areas of the detector. Okay, so I have specified already these 2 different dithers. So what you know, let me just get rid of this so you can see. This is what when you select fixed dithers, the table comes up like this. It grays out the fact that you've already got 1 dither point. That's the central dither point. So you're basically already getting 1. So you add any more. So this will be, I added a second one, and I'm going to give it a dither of 15 shutters, just to demonstrate how this works. So I'm going to have 2 MSA configurations, and it tells me that right here, below the table here. Okay, so I'm happy with that. I'm not going to discuss this right now. It is a little bit complicated to talk about right now. I will try to go back and remember to talk about that. I'm going to select the Prism. I have choices here. I have a lot of choices between gratings and filters, but I'm just going to show you an example using the Prism. The Prism has shorter spectra, and so I should be able to get more sources onto the MSA without contamination. It automatically populated my search grid with a center and a width and a height, and those are based on the size of the candidate set for the primaries, I think, or on the catalog. I'm actually going to limit the selection a little bit. These are editable parameters. I'm going to make it 200 by 200 for my search grid, and I am going to keep the step size of 5. I think when you first start from scratch, it says 30 arc seconds, but I'm going to use a smaller separation. There's about 1,681 pointings. If I change this to a different number, like 3, and then click out of it, you'll see that it figures out how many pointings you have. So I'm going to use, like I said, 5. Okay. And this, I'm going to click off these parameters here. I'm not going to use target weights right now. I want to show you the difference between using them and not using them. So I'm going to do my first plan with not using them. Again, because I have 2 dither points, 2 fixed dithers, I need 2 configurations minimally in order to derive 1 target set. Now, the reason we give you a chance to enter more, and it has to be, in this case, it tells me multiples of 2 in order to get a complete target set, because I need to complete the plan for those 2 dithers each time. So the reason we give you the option to add more, like 4, 6, 8, is because then you'll get more target sets. You'll be able to observe more of your primary targets from the list of primary targets that you've gotten, that you've specified. I'm just going to put 2 just to show you how it works. It will tell you if it's used this name in a plan that you've already developed, it will tell you, no, you can't use the same name. So it forces you to rename this. So I'm going to call it 2 dithers and Plan A. You have to click out in order to activate the Generate Plan button. So now I'm going to click Generate Plan. So it's working on looking at that test grid, that search grid, and it's trying to figure out, for the 2 dithers that I've specified, it's trying to find a good starting point for those 2 dithers, which picks up the maximum number of sources. So it's come up with a conclusion. It pops me right over to the plans pane here, and that's where you do the plan assessment or evaluation. Now you can see I've already played around with this. I've already had 2 plans already. I'm just going to be repeating live for you what these 2 plans show. So, okay, I must have used a different set of parameters in the planner here. I think I used a different dither actually previously. So you see there that there are 6 exposures in this plan. There are 46 primary sources that this plan observes, and 125 secondary sources or fillers that it observes. So this is just a status line for each of the plans that you develop. So it's a quick way to compare the plans. Let's see. You can export the plan itself and share with other members of your team, and this Replan button is used to, for instance, if I click this, it goes back to the planner. It remembers the plan parameters I used last, and then I can tweak any of those parameters. So, for instance, if you were in the final phase of your planning for your program update, you would switch to the aperture position angle that you were given as your assigned angle. And so Replan is a quick way to do that. But I'm going to go back to the plans pane. And so now I've shown you how to do it without weights. Let me just investigate all the other information that you have available to you in this pane. So eventually we're going to select one of our plans that we like the best, and we're going to create an observation from it. That's what that button is for. You can export a plan and import plan here. You can also describe a plan. So I have one. I'm going to highlight the one we just made, and I'm going to click Describe Plan. Describe Plan shows me what all the plan parameters were that I used for that particular plan. It helps you keep track. That out. And then, of course, you can delete any plans that you don't want to maintain there. Okay. So with the plan that I've highlighted here, it has 6 exposures. It has 3 exposures for the 3 node positions in the first configuration. And in the second configuration, it's got the 3 node positions. So it's got a total of 6 exposures. It says configuration 1, exposure 1, node position 1. The next one's node position 2, the next one's node position 3. That's what that nomenclature there means. It tells you what the plan number is. It's from plan 3. So you can keep track of what you're doing. Gives you the RA and DEC of the pointing, and in a different format here, the aperture position angle, the grading of that exposure, and then the target set size. This is the total number of targets from your list that were observed, so both primaries and fillers. And it gives an indication of the total weight based on the weights of the sources that you have picked up from your different candidate lists. If you click, let's see, how do I do this one? So I'm going to just, let me just review what's down on the bottom of the page before I show you some of these buttons. So below, whatever's been highlighted here, so I have the plan highlighted above, that highlights all the exposures in the plan, and now I can filter the target information from these exposures in different ways. I can ask to see all of the primary targets that make it into all of my dithered exposures, and it tells me there are 46 targets. And it lists those targets down below. Each of the targets has a weight that's recorded here, and the number of exposures that target is in is listed, 6 here, all 6, because that's specifically what I asked for. What are the targets in all exposures? And, okay, so let me just do this. Let's try the filler targets. So there are 100 of those. And the MSA Planning Tool will try to optimize the number of both primaries and fillers. Fillers are no longer one-off, which means that they're not filled, they're tracked in order to be able to put into the plan consistently for all the dithers. And the same goes for the primaries, of course. So the pointing positions that were selected for the plan actually only depend on the primaries and being the completed primaries, those that make it into all the exposures. And remember, there was a parameter in the planner I didn't want to talk about right away because it is a little complicated, and that is this box right here, partially completed sources. This is a new feature, and if you select it and then do the plan, what it actually does is it tries to populate. You also get a choice of how many minimum number of dither points that you want to have exposures of your sources of. So what this does, if you click this, is it plans first for the completed sources. It derives the best pointing for the completed primaries. Then it makes another iteration, and it goes back and it looks for primaries that aren't quite completed at all the dither points, but are at, n-1 dither points. So if I had 5 dithers in my table here, it would look for, after it's done picking the pointing from where all 5, you know, where the sources are in all 5 exposures, all 5 data points, then it will go back and try to do the same thing for 4 data points, and then 3 data points, and 2. So you can control how far it goes with this box here, for example. So that's how that works. And so when I look at the plan results again, then the view of the views that we provide here of the targets, you'll see partially completed targets through all of the table that you see here when you do that. I'm not going to show that today. But in this particular case, the histogram is very simple. It's because all the targets are completed, and all the targets that listed are about 100 targets that are all completed in the 6 exposures. So that's what you're looking at here. Now, I said I would go back and show you what these buttons do, and I'd like to do that. I'm going to click Show. This brings up the MSA Shutter View. It's a view of our primaries and our fillers on the micro shutter array. It's a sketch. So what I'm doing is I pull the corner of the box out in order to be able to enlarge this view. You can click the left mouse button, drag, as you normally would. On my trackpad, I just move my fingers up, scale to zoom in, so that I can see what I'm looking at here. So remember that this is for a Prism Exposure. So what we're showing here in green are the primaries, blue are the fillers, sources that are being observed in this exposure. Black, as you see one hidden here, is a contaminant. There's another one here that's got into the slit of the primary sources that I've indicated here. So there are a few contaminants in this view. It tells you where they are. It also shows these light orange areas. The light orange areas are the masked regions around each source, where you cannot place another source without getting spectral contamination. So it indicates to you what areas of the MSA are still available for use if you'd like to do that, if you had any more sources that you would like to fill in. So I'm gonna zoom in a little bit more here just to show you. So when you see a lot of orange, that means it's utilizing the real estate on the MSA very well. And that's its goal, is to do that. I also wanted to point out you can overlay your candidate sets or your catalog. I'm just going to do the redshift greater than 5 sources. So it plots on top of those that have been observed, it plots the remaining sources, which it couldn't observe these at every one of the positions, the node positions, or at any given node position, because it may be able to observe these sources through 1 or 2 exposures, but not through a complete node set. So that's why it didn't pick up these other black sources here. And most of them are actually falling on an area which would be precluded from being used anyway, because another target occupies that area. So that's what you think. In red here, the light red is where, remember I told you we mask around the open shutters, the failed open shutters, which are shown. I'm trying to show this from up. I'm trying to scale up. Scaling is not working. Okay. There we go. So this is one of the failed open shutters. It has a large area around it being masked out. So that's what you see there. Okay. And there's a few others. That's why this one's so large, because there are 2 in that area. Okay, so there's another view. It's called the collapsed shutter view, and it also shows the primaries, the fillers in blue, and the contaminants in black. The contaminants are falling in an area outside of the constrained margin. You can see the constraint margin that we use is shown in white here. Remember, I did midpoint as my selection for the source centering constraint. All the legitimate sources fall within that white dashed area here. But the contaminants do not, because they're just being picked up by whatever's open, commanded open for the other sources. Okay. If you hover over any one of the sources, you can read its source ID. Let me go back to this. It's also possible, let me just zoom down again to show this. It's just a little slow. Okay. Getting there. Okay, so another thing that you can do is you can return to your APT window, wherever it went there, your main GUI window, and the other one's still there. And I can go down to the targets area. Remember, I'm just highlighting one exposure at this point. And I can, so what I can do is I can show another one. Let me show the second configuration, for example. I click Show, a new window pops up. Okay, and then I have to show you, I'm sorry, this is hard to see with all the windows, but it's better on your desktop. I'm going to shrink this a little bit so we can see things. Oops, wrong way. Okay. So these are the two different dither positions. It's showing the first exposure of two different dither positions here now. So I can actually go here. I can highlight both of these exposures, the C2E1N1 and the C1E1N1, and then I see down below all the targets listed for those two exposures. I can click Command A to pick up all of these targets, and you can see that these sources are highlighted in these exposures here. So it's a good way of tracking, you know, when sources are visible in different exposures. You can only have two of these MSA shutter views open at a time because it requires a lot of memory, and we had to limit it to just two. Okay, let's see. So you can filter the information from these exposures that you have highlighted. You have to highlight them in order to filter the information down below. As you can see, I'm only showing the two that I highlighted. And so other ways of filtering information, you can say, okay, what are the targets that are missing from one or more selected exposures? And it shows you these are the targets that are in one or the other of the two highlighted exposures, but not both. So there's different ways of filtering and looking at the data there. Okay, so now I'm going to go back to the planner. It's going to remember the parameters that I had from the last time I ran the planner, which is nice. I'm going to keep everything the same, but now I'm going to use weight, target weight. And in my catalog, I'm going to click weight. Okay. And I got to give it a different name. I'm going to call it weight A, I guess. Click out of the box and then click generate plan. And we're going to look and see if this plan is any better in terms of the number of more highly weighted sources that we wanted to observe more than others, to see if the plan has more of those in it. Okay, so we still have the other plan. This one and this one are the two that we're comparing now. It looks like we have the same number of primary sources. We have fewer secondary sources. Now let's look at, keep your eyes on total weight column, and I'm going to flick between the two different ones. Total weights here are about 11,000. Total weights here are more than 12,000. That's because it's picked up some additional highly weighted sources. In this particular catalog, I have, let me go back to this. Let me go back to this. So in this particular catalog, I have sources with the highest priority sources are weight 300, and then everything else is below a value of 30. Just the way I put it into the column there, the weight column there. I can sort by the weight, and you can see the number of highly weighted sources that are in there. So it's picking up at least a few more of those, I think, in order to get the higher weights in the plan. So this is what I would consider to be a better plan than the previous plan. Even though there's fewer filler sources, they are secondary sources, and I'm getting more of my high-weighted primary sources. So that's what that's all about. Let me just check my script here to see that what else I need to show you. Okay, so from the MSA shutter view, I wanted to show you a neat little thing. You can send shutters to Aladdin. Now this is, again, just one exposure being viewed here. I'm going to send the shutters to Aladdin. Let's see if this works. It shows now here, I have to zoom in so you can see this, but I had an image that was already loaded there. Oops, let's put the zoom. I had an image already loaded of this field. And so what you're seeing here are, here's a few probably good sources you can see. So you can see that these shutters are overlaying sources that were in the catalog that I selected for observation. So that's one of the things, one of the nice little features that it has. Let's see what else I'll show you. Let's select this plan. So, okay, so now I'm returning to the main APT window. I'm trying to drag it down. Okay. And it looks unfamiliar, right? Because it's still in the Aladdin view because I visited Aladdin. So whenever you get lost, click Form Editor. That brings you back to wherever you were. So, so we want to go to the MSA Planning Tool again. And we have the plans here. I'm going to select this plan as the one I'm going to create an observation with. So you can see that it populated the observation folder with an observation, and I went over to the observation. I'm now in the form editor. Again, I was in the MSA Planning Tool to select the plan and create the observation, but it automatically changed the view for me back to the form editor. Now I'm in the observation template, and this is where I would want to fill out the rest of my parameters for the observation. You'll notice that there's a red X right away, and that's because the planning tool doesn't require full knowledge of how long you're going to look at these objects. It just needs the positions of the objects to do the plan. So now you have the ability to change or, select your duration parameters here based on whatever you find in ETC are the best parameters to use. For this observation, I'm going to put 20 groups and 1 long integration. Okay, the red X went away, and let's see how many visits we have at 1 visit. So that's all good. It tells me, of course, that I'm using the MSA target acquisition. It will require the definition of reference stars in the later phase of the proposal or the program at that point. It's populated all the information from my planner, from the planner over here, or from the plan over here into the observation template, and that can just all stay the way it is. It told me what my primary and affiliate candidate list was, and that's the angle at which I use to run the planning tool. And so my advice to users, our advice is that you run the planner with lots of different tests of feasible aperture position angles so that you can evaluate how successful each plan is and whether you need to pad the, your times, your requested times based on the efficiency that you're getting from whatever strategy you're using. So it's something that you can see if there's preferential angles. If there really is clearly a preferential angle, and it's because of a very non-symmetric distribution of sources on the sky, for instance, then maybe it behooves you to specify a special requirement with an angle preference that you want, and that will be weighted against all the other programs that don't have that special requirement. So it is something we like to discourage users from doing, but it is available to those users that have, very, very distinct source distributions on the sky. So here in the observation template, there are 2 tables. There's an exposure specification table, which basically gives the grading and filter and the exposure parameters, and then these are the 2 configurations for the 2 dithers that I created. And it's got, it tells me the exposure specification. I can't change it because that's the only one I created my plan with. So that's good. And then and it tells the pointings for the 2 dithers, and then it gives you the ability to specify other dithers here, but that's usually used for when you're not designing the plan automatically with the MSA Planning Tool. It's for building an observation completely, custom observation separately. So I wouldn't touch that. It tells you it's using a 3-shutter slit-lit nod pattern, and let's see, total integrations of 3. Because of the 3 nods, and the total exposure time is here. And then I can actually modify this MSA configuration. If I click Edit, it's bringing up configuration 1, just like the MSA shutter view in the planner, in the plan. I can expand it. I'll just show you how to modify this. Zooming in. So say, for instance, I didn't want this source. I would just click each shutter, and it closes. Oops, sorry about that. It closes that shutter, and it opens up this real estate on the MSA for any other source that may fall in that area that you perhaps want more than that source. So you can modify the configuration and commit the modification to the observation. Let's see. You also have the ability to specify whether or not you want to open a bunch of random shutters to create a master background for processing your spectra. You would click this button and then continue to open shutters here and there in available areas of the MSA in order to do that, but I'm not going to do that today. Okay. Thank you very much for listening to this video. I hope you found it useful and that you will be planning your MOS observations in the very next cycle.